molecular vibrations. So molecules and their bonds vibrate at certain frequencies, and you can absorb photons of energies that correspond to those frequencies, and that can be detected, and that's what we're going to be talking about. In second semester, we'll look at NMR spectroscopy. This is the same idea. You're going to be looking at transition, but here it's a transition of magnetic moment of a nucleus in a magnetic field flipping from spin aligned to spin anti-aligned. So it's you're still looking at an energy transition. And how this works is when you basically shine light at a sample, it will absorb the light that corresponds to the energy differences in these states. So if you're looking at UV, you're looking at the energy level between a bonding and anti-bonding orbital. And when you irradiate that sample with that energy of photons, the electron gets promoted and the photon is absorbed. What that means is that if you're sitting on the other side of the experiment, you're looking at the photons that pass through. They'll be passing through, but where it absorbs it, you'll have a decrease in the number of photons that go through the sample. At its core, that is the entire spectroscopy experiment, is you are shining light through a sample and detecting when those photons are being absorbed. The various energies of photons are going to determine what type of transition you're looking at. So as I mentioned, X-rays, you're typically looking at sigma bonds. With ultraviolet and visible, you tend to be looking at non-bonding and pi bonding electrons. IR, you're looking at vibrations, so bonds can vibrate like this, and it's sort of a simple vibration. You can imagine two balls on a spring, but then they can also do other weird things like their scissoring movements and all these. And all those have characteristic energies that depend on the structure of the molecule. So as you basically scan through the various energies of photons, you get a readout of what vibrations are active in that particular compound. And so that's a spectroscopy experiment. Incidentally, NMR, when we do that, those are way down here in energy. It doesn't take a lot of energy to just flip a spin in a nucleus. So that's a pretty weak interaction. So just to remind you, this is, we're talking about light. It has a frequency and a wavelength. Depending on what kind of spectroscopy you have, it will describe the photons in alternatively in wavelength or in frequencies. And just to remind you, the sorts of scales you're looking at here, this is wavelengths of like visible light. You're in the hundreds of nanometers as far as the size of the wavelength there. Whereas in radio waves, you're at close to a meter of wavelength. So that's going to be considerably longer. And then X-rays and whatnot would be at very, very high, small wavelength and high frequency. So again, this is kind of giving you a summary of what the different spectroscopies are and what type of transitions you look at when you are probing a sample with that particular radiation. And again, this chapter we're going to be looking at infrared, and here it's vibrational energies that we're looking at. So as I mentioned, these energies, they're not all just simple two balls on a string vibrating and it absorbs a photon so it vibrates faster, or it vibrates the same but bigger amplitude. There are stretches that can go, say if you have two bonds that are interacting with each other, you can have stretches where they stretch in opposite directions at the same time. You can have them where they go in the same direction all the time. And this is all in general, a fairly complicated type of system to figure out what the exact vibrations are. Fortunately, we're not going to have to dig into it anywhere near that far. What we are going to basically do is see how this is useful for identifying functional groups in a molecule. So infrared spectroscopy is one of the older spectroscopies that gives high resolution data. So UV and IR spectroscopies were some of the first ones. UV peaks tend to be very broad and not giving as much fine detailed information. On the other hand, in the infrared, you see you can have broad peaks, but most of the peaks are reasonably sharp, and some are actually quite sharp and quite strong. And what's been found is that these peaks correspond to particular functional groups and their vibrations. They're characteristic for that functional group. So what happens is that you can take a IR spectrum and almost immediately begin to check off a list of what functional groups are present in that molecule. As far as how we're going to approach this, we are going to do something kind of similar to this, though you're going to have a very limited set of vibrations. As you can imagine, with any sort of molecule that's reasonably complicated, there are lots and lots of combinations of vibrations that can occur. And then just to make everything more complicated, these vibrations are kind of like strings on a musical instrument, and you can have overtones and whatnot as far as that goes. So you get second order effects, not just the original vibration. But having said that, again, it's a very simple experiment to rationalize. You take a UV source and you shine it through the sample, and it hits a detector after it passes through the sample. And what you're looking at is where are the photons being absorbed. Now the typical IR spectrum is kind of drawn in a weird direction for that. So this is, in organic chemistry, they tend to have 100% transmittance. So 100% of the signal going through is at the top, and a peak pointing downward is a stronger and stronger absorption, because this is transmission. So 100% transmission would be up here, 0% transmission. In other words, the sample absorbed all of the IR radiation at that frequency. That is shown as a downward pointing peak. So it's kind of upside down from what you're going to see from most other types of spectroscopy, where you have absorption going up. And then the other thing that's weird about this is that the x-axis is going to be frequency, but instead of using sort of normal frequency units, it uses wave number as a frequency unit, which is the reciprocal of the wavelength. Wavelength and frequency are inversely related to each other. And so when you take the reciprocal of the frequency or the wavelength, you're getting a frequency scale. So a larger wave number is a higher frequency. And specifically, the wave numbers are, units on wave numbers are per centimeter. Or reciprocal centimeter. So this is what a sample might look like. And typically, an IR spectrum for organic compounds will span the range from about 4,000 reciprocal centimeters to 400. That's sort of the window that you look at. This molecule is fairly straightforward. You have a number of CH bonds, and then you have a carbonyl group on this ketone. And from this, you're supposed to be able to come up with that. Back even before my time, IR was the best structural method there was, and you had people who you could basically just show them this, and they probably would have sketched the molecule out for you just based on the information here. NMR spectroscopy is much more valuable and much easier. It gives you better information, and so that's really very much a lost skill. But there are a few places in the spectrum that you can look that give very diagnostic peaks. So for example, this very sharp peak here is at about 1,700 reciprocal centimeters, and a sharp peak in that region, say from about 1,600 to 1,750, 1,780, something like that. But basically in this region, that's where carbonyl stretches come. That's where you have a carbon-oxygen double bond, and that's looking at the stretch of that bond. It is very diagnostic for that bond because there's actually very little else that absorbs at that location. And this is also a very strong absorbance. It's typically something that looks like this, where it's the most prominent peak on the whole spectrum. So even for somebody who can't really elucidate structure that well with this, with a little bit of knowledge, you would be able to recognize that this, whatever this sample was, must have had a carbonyl group. It must have had a carbon-oxygen double bond in it. And there is more information you can get from it. An aldehyde will have a little bit different frequency than a ketone. They both have different frequencies than carboxylic acids and esters and all the functional groups that contain those. But that is a very diagnostic peak for carbonyl groups. Kind of up here in this range, these are typically CH stretches. They're kind of centered on 3,000. So the 3,000 is here. You can see in this case that all the peaks are a little bit less than 3,000. That not only tells you that this is, and this region is typical for CH bonds. This tells you not only do you have CH bonds, but there's CH bonds to sp3 hybridized carbons. If you had a peak just above 3,000, say 3,050 or so, that is indicative of a CH bond with an sp2 hybridized carbon, so an alkene essentially. So this area right here, kind of in the 2,900 to 3,100, gives you information about what kinds of carbon-hydrogen bonds you have. And you can have both kinds in a molecule. If you have alkenes and alkanes in a molecule, you're going to see some absorbances below 3,000 and some above 3,000. They'll both be represented there. Finally, the one other signal that we're really going to deal with that's very diagnostic is an OH stretch. So like you would have in an alcohol. OH gives a broad absorbance, but it's very strong and it's way down here. So typically if you have a hydroxyl group here, there's going to be a really wide peak, and it'll be probably about the furthest thing to the left on your spectrum. That's basically the palette that I want you to be able to work with. The kind of question I'm going to give you is similar to what I gave in the practice problems, which I'll look at in a second. This is going to, that will be the type of problem you have, and you're going to be able to solve the question by using these essentially 5 frequencies. So if you see a peak at a frequency for a particular functional group, it's present. If you don't, then it's not. So this is a little bit more of a complicated picture here, but OH tends to be over here, CH tends to be over here a little bit, NH is actually kind of in between. Carbonyl groups, again, are the strongest thing you see around 1700. Carbon-carbon and carbon-nitrogen double bonds are nearby. So there's a lot more information you can get from this, but I really just want you to kind of dabble in this a little bit. I want you to understand the value of this in terms of being able to choose between samples with perhaps similar properties, but slightly different functional groups. So the ones that you really need, that you guys really need to pay attention to, are going to be the OH, and typically these are very broad, and they tend to be very strong. This says strong to weak to strong, but I'm not going to give you anything that has sort of a puny OH peak. This is usually something that just looks huge. If you had a OH group here, it would tend to look something like that, or even larger. It's very hard to miss it. So OH will be one group. The carbonyl group will be a second group that we will look for. Those are 1630, 1820, so that's centered on about 1700. This is probably centered around 34, 3500. And then finally, the other frequency that we're going to be playing around with is the CH, and that occurs between 3300 and 2700. And the rule we're going to have for this is if you have greater than 3000, then it's an sp2 carbon hydrogen, and less than 3000 is an sp3 carbon hydrogen. So you basically just need to know about where these four frequencies lie. I'm not even going to give you a spectrum to look at. There might be some of that in your homework, but on the exam I'm going to give you the number written out. You just have to remember what the functional group is, and then deduce which structure goes with which spectrum. So for example here, this is a hydrocarbon. It doesn't look like I have the full spectrum here. There's nothing large and broad up here that would give you an OH. Here's 1700, so there's clearly no carbonyl group. This is 3000. You have some CHs below 3000. That would be a sp3 carbon. And this is actually sp. It's a little bit further down even than sp2. But this is kind of giving you some idea of how that will work. And like I said, we're basically just going to say if it's above 3000, it's sp2. I guess it could be sp as well. And if it's below 3000, it's an alkane type of CH. Different carbonyl groups will give you different frequencies for the CO stretch. You don't have to really dig into these differences. You just basically need to know this is around 1700 and have an idea of what the window is. It's 1700 plus or minus maybe 100. And you can see that there's a lot of them, but you can get pretty specific information about functional groups from where this actually is. But when you have an actual compound here, this one is a ketone. If you look at the structure, you should have a carbonyl group, and there it is, right smack. It's a ketone, right smack on 1700. It's strong, and it's, like I said, it's usually the only thing that you're going to see in this part of the spectrum. The CH here is 3000. All of the peaks, so look at where the peaks are, not where the shoulder is up here. All of that is below 3000, so there are only CH groups from sp3 carbons. So that's what you would expect to see from this structure. And that's the level of analysis. So you should be able to match this spectrum to that structure, provided I give you information that's different enough to do that. So having said that, if I kind of skip to the end of this, this will give you an idea of how I might ask this. So basically I give you 4 structures and 3 sets of IR data and ask you which IR data goes with which structure. Basically I put you in a lab and you have mislabeled vials, and you know what the vial, you have 3 vials of something, you don't know what they are, but you don't know what's in each vial, but you do know what it could be. So each vial could have one of these 4 things in it, and so you take IRs to figure this out. The way that you should be approaching this is you can almost think of it in terms of what do you expect to see in a given molecule. So this molecule here on the bottom is an alkane, it's a cycloalkane. It only has CH bonds in it, and all of them are sp3 carbon H bonds. So what you would expect is a CH stretch just below 3000. And in fact, you're going to have that in all of these because they all have sp3 carbons with CH bonds. And they will all have that. So that's not really going to tell you anything about this. All 4 of these compounds have those. The one that's different is this top structure. You do have sp2 carbon with a CH, and you would expect that this would be just above $3,000, maybe 3050, say. And those would be the two things that you would see, and this top sample is vial 2. Vial 2 has 3050, which is a CH for sp3, and excuse me, sp2, and it also has 2970, which is sp3 carbon. That's CH bond. So that's how you're able to assign the vial 2 is that particular compound. The two in the middle have carbonyl groups. This will be carbonyl group around 1700, and we're not putting too fine of a point on it, so this will be around 1700, give or take 100 or so. But the other thing is this has an OH, and so you expect something like a 3400 for an OH. Vial 1, 3450, 2970, and 1720. So this is the OH group, this is the C double bonded O, and this is sp3CH stretches. So vial 1 is this compound. And then the last is 2970 and 1705. That's a carbonyl. That's a sp3CH. So that's going to be this compound. So it turns out that this was not in any of these vials. So basically, you just have 5 frequencies to frequency ranges to kind of assign and know what functional group it is. And then the rest of it is just, you can assign what you think the structure should look like and then look at these. Or you could come over here and say, okay, that's sp3CH and a carbonyl. This is sp2CH, sp3CH, and you can assign them and then go back to the structure. Either way you want to do it works. But you will have a problem that looks kind of like this on your exam. The point is that these functional groups vibrate at very specific frequencies that depend on a lot of factors: the sizes of the atoms in the bonds, the strength of the bonds, the various changes in dipole moment as the bond vibrates. All these things come into play, but there are some very, very diagnostic regions in IR that allow you to quickly identify functional groups. And if you ever needed to do this for real, then obviously there's a much, much larger palette of frequencies you can look for. But we're doing this just so that you have a sense of what you could do with it. So congratulations, that's it for Organic 1. So, 12 chapters in 21 days or something like that. Any questions on IR spectroscopy?
So would that bottom molecule only have one reading, so it would just be below 3,000?
Yes. Now, the spectrum, if you looked at the whole spectrum, there'd be a lot of peaks, but I'm basically cherry picking the ones that are going to be diagnostic to you. Yes.
Would you be able to tell the structure by just looking at those peaks?
How much of the structure?
Okay.
Yeah, that's the problem with it, is that, yes, there is a lot of information that you can get out of it, and like I said, there were people who look at these, IR spectra and be able to give you a good guess on what the molecule was. Usually it helps if you have a formula, so you can kind of limit it a little bit. But, you know, whether they'd be able to tell between, ethyl cyclohexane and dimethyl cyclohexane is a little bit hard to say. There are going to be some vibrating modes that are different in those from having two methyl groups. And there are weird things that occur, like I said, you can have two methyl groups with CH bonds, and they could be doing this symmetrically or non-symmetrically, or wagging back and forth, and there's just, all those are, have a frequency and have an energy associated with them. Yes?
On the exam for the last one, would we be expected to, like, if we didn't match it to any of them, we'd have to write like CH below 3000?
No, all I'm asking you is to match the vial to the sample, or to the structure.
If it doesn't match one.
I'm sorry?
If it doesn't match any of them, we just leave it blank.
Yes. I mean, I think I gave you like the same 3 vials and 4 possible compounds. It seems not quite sporty enough to give you just 3 compounds and three vials. Has to be a little bit challenging. Anything else? All right, so, you want to see practice problems? Oh, ready? So I am assuming that all of you have worked these, so, all right. So, naming this compound, your first thing, of course, is you're looking for the parent chain, and it's the longest chain with your highest priority functional group, which is alcohol here. And there are 2 ways that you can do this, and they're equivalent. But that is your parent, and you number from the end closest to your alcohol. So this is an octanol, and specifically it's a 2-octanol is the parent. So that means that you can eliminate A, B, and E. Since the C and D are the same, except for the configuration of the chirality center, to work this problem, you really only have to do one other thing. But just to finish naming it, you have a 5-methyl substituent, and then this substituent over here is a sec-butyl substituent. And it's attached to the 4 position. Sec-butyl, it's a 4-carbon, it's basically a butane, but it's attached on a carbon 2, which is a secondary carbon instead of the primary carbons on the end. If it's on one of the ends, it's just a butyl substituent. Okay, so the configuration of your chirality center, you have to assign the priorities. The OH group is 1, this carbon has a carbon and 2 hydrogens bonded to it, whereas this carbon has 3 hydrogens. So carbon beats hydrogen, so that's 2 and 3, and the other group is the hydrogen in back, which is 4. It is clockwise with the lowest group in back, so it is R. So that would be that. Ethylene glycol is one of our common names. That is the structure of ethylene glycol. You don't have to draw the skeletal structure, you can do it as a condensed structure. Rubbing alcohol is not just common name, it's a what's more common than a common name?
Colloquial?
Hmm?
Colloquial?
Colloquial? Oh, okay, that works. At any rate, rubbing alcohol is isopropyl alcohol, or isopropanol, or 2-propanol. So there were a couple of those that we had. We had wood alcohol was methanol, grain alcohol was ethanol, and rubbing alcohol was isopropyl. Antifreeze was ethylene glycol. Though I don't know that of anybody who really points at a bottle of ethylene glycol and refers to it as antifreeze. It's just one of the main components of all antifreeze. So it's that's just kind of a colloquial way to refer to it. All right, so predict the products. And we have optical activity here. So you have phosphoric acid, which is a strong acid, and you're told that this rearranges. So what the problem here is that if you have a strong acid and an alcohol, you can protonate the alcohol to make it a better leaving group. But if this falls off, you have a primary carbocation, which is extremely unstable. And that is why this would rearrange immediately. If you do a 1,2 hydride shift, what you end up with is a tertiary carbocation, and this H that hopped over is on here now. From here, the rest of the way would be to eliminate, finish the elimination. This is an E1 type of mechanism. You don't have a good base, so you can't really, you wouldn't really want to say that this is an E2. And there is basically no nucleophile around, so it's not you're not just doing a substitution. So from this carbocation, you could potentially make several alkene products. So if you're just looking at where you have beta hydrogens, there's the one on the top, the one on the bottom left, and then the one to the right. So this is That's one, that's one. This is two, that's two, and three is this direction. First of all, hopefully you recognize that 1 and 2 are the same thing, so you don't want to draw both of them. Second of all, you should recognize here that this is going to prefer the Zaitsev product, which is the more highly substituted alkene. Number 3 is the tri-substituted. You have carbon, carbon, carbon versus carbon, carbon, and carbon, carbon. So the more highly substituted product is preferred there. The correct answer here then is this alkene. Finally, optical activity. The alkene functional group is flat, so there is no chirality there. There was chirality with this methyl group at that center when you started, but when you made the carbocation is flat, and so your stereochemistry, that information is gone at that point. Because this carbon had stereochemistry, this one is flat and it can't have stereochemistry. And so that's how you get to a non-optically active product. If it's an alkene, it's not optically active because it's achiral. If it turned out that it had a chirality center still in the molecule, it might be optically active if you get it up with 2 diastereomers, but it's not optically active if you just have the one and it switches. If you have equal amounts of the two of them, of course, that's racemic and not optically active. Some of the problems, incidentally, I did ask for optical activity. Some I just asked you to draw all the isomers of the product. All right, so Swern oxidation. You should recall that Swern is going from primary alcohol to aldehyde. And secondary alcohol to ketone. Here we have a primary alcohol, so the carbon skeleton stays the same, and this carbon is now going to be your aldehyde carbon, and you're done. If it's one of these reactions that just works at the, at one part of the molecule where the functional group is, the rest of the molecule stays the same. This is optically active. You had a chirality center here, and you still have a chirality center at the end of the day. The reaction doesn't touch that. Okay, PCC was pyridinium chlorochromate. This oxidizes primary hydroxyl groups to aldehydes and secondary alcohols to ketones. And that basically means that this is going to look exactly the same. And it would be optically active. So it turned out here I gave just 2 different sets of conditions that gave the same reaction. Such things are possible. We have at least 3 ways to make aldehydes from primary alcohols. I could have given you Des Martin reagent here as well. The only thing that would have given you something different was chromic acid. And I think we're calling that H2CrO4. And that would have given you what?
Carboxylic acid.
Yeah, you'd have the carboxylic acid, so instead of a H here, you'd have an OH here. Secondary, you still get a ketone. But primary, you would get a carboxylic acid. It can't stop at the aldehyde. So these cases where you have multiple reactions doing the same thing, you still need to learn them all because you don't know which one you're going to get. But you can kind of simplify it a little bit by saying all of them do the same thing with a secondary alcohol, and then the outlier is the chromic acid with the primary alcohol that gives an acid. Everything else gives you an aldehyde. Okay, so D, we have a tertiary halide and we have a strong but sterically hindered base. This is the classical setup for an E2 elimination, provided that you have a beta hydrogen to take with this. This carbon has 3 methyl groups on it, so this carbon does not have a beta hydrogen. This carbon also has 3 methyl groups on it, no beta hydrogen. The hydrogens out here don't matter, it has to be on the neighboring carbon. This methyl group, however, has 3 hydrogens on it. This is beta to your halide. So the only place that this elimination can go is there, and your products would be predicted to be this. Again, you want to recognize what functional groups you have and the reagents. Potassium T-butoxide almost always gives you an E2 elimination. Probably you'd be safe saying it always does. If you have a smaller base, then you have to worry about other things occurring. Substitution, for instance. But in the case of potassium T-butoxide, that is a very, very standard thing to give you an E2. The only other thing I would say is be aware that sometimes you will see it written like this. Potassium T-butoxide, so it's kind of out of order there, but this is a superscripted T for T-butox, the T-butyl part. Yes.
If one of the other beta carbons had a hydrogen, wouldn't that still give you the non-Zaitsev product?
So if this is a hydrogen here, then the Zaitsev product would be that, and this would be your major product.
But wouldn't the bulky base give you the non-Zaitsev product?
No, it's It can be a little more complicated, but we're basically simplifying it. It's gonna give you the Zycev product in our world. You go in the lab and do it, it might not, but we're kind of, going to stick with, the 20% of the work that gets 80% of the answers. So yes, with a Voki base, it's, could be difficult, but, you know, how much more hindered is this compared to one of these CHs?
Yes. Would you want us to draw both or just the Zaitsev?
Zaitsev. If there's really no preference, say you had two different, I don't know what, don't wanna riff on this too much, but, you know, if it was like this and this, I would want you to draw both of them, but you would not need to draw that. So where there is a preferred product and it follows Zaitsev's rule, you should give me the Zaitsev products. Just like we did with Markovnikov's rule. Both of them aren't right 100% of the time, or you don't get 100% of one and none of the other. Some of the time you get 80-20, but again, we're looking at what the majority of it is. All right, so next we have a chiral alcohol. Oh, and these are not optically active up here. Because it's flat. Okay, so we have an alcohol and PBr3. You should remember that what this does is it replaces the OH with a Br, and it does it with inversion. So all you do is slap a Br on that that's coming from behind instead of in front, and you say it is optically active because it's inversion, and you're done. Some of these problems are really that simple. You have to recognize what the functional group does with that reagent, or however you want to think about it. And the first answer is to get the bromide there. The second part of it is the stereochemistry, but those are the only two things you need to worry about with PBr3. Is it converts an alcohol to a bromide with inversion. All right. So this is when treated with potassium T-butoxide, the cis and trans isomers of the cyclohexane below give different products. Explain. Well, these are usually, if you're getting a non-Zaitsev product, so the one on the left is non-Zaitsev, it's only di-substituted, and this is a tri-substituted. So if everything was free to rotate everything, it would give you the one on the right. You would expect the Zaitsev product. And the cis isomer gives you that. The trans isomer gives you something different. That fact and the fact that you have a 6-membered ring involved here means you need to look at the chairs. Now, drawing this can be simplified by the fact that when it eliminates, the bromine is going to be axial, because to be in the right geometry to eliminate it is going to have to be, axial, and the hydrogen is axial on the next carbon over. So they are both at, the hydrogen that's being eliminated and the bromine group are axial. So you might as well just draw the bromine in an axial position and then ask are there hydrogens that are also axial. So here with the cis, your methyl group is up on that carbon, and you have a hydrogen which is down, and here you have hydrogens there. If I'm going to take these out so it's not as busy. So here, because the methyl group is up and the hydrogen is down, this and this are both diaxial on neighboring carbons. On neighboring carbons, one's going to be up and one's going to be down. So that's in the right geometry. That's the direction you want to go to make the Zaitsev product. So that's what happens. There is a hydrogen over here that is also axial, so that is possible, but that would be the non-Zaitsev product. So geometry-wise, it can eliminate both ways. Zaitsev-wise, it only goes there. On the other hand, if you look at the trans, and again, I'm going to go ahead and draw the bromine axial because it has to be axial. If it's trans, then you have hydrogen up and methyl group down. This hydrogen is not anti-coplanar with the bromine. In a six-membered ring like this, if that is pointing up in an axial, the hydrogen has to be down on an axial, and here you have a methyl group. So that's why this doesn't eliminate that direction, because there's no axial hydrogen here. On this carbon over here, the other one sort of in front, there is an axial hydrogen. So this and the bromine come off, and the double bond is, this is where your bromine was, is that carbon. This is the one in back, and this is the carbon in front as I have it drawn. The orientation of this doesn't really matter, and it doesn't matter that you have the bromine pointing up. Remember, I didn't say whether it was up or down to cis and trans. Just put the leaving group axial, and then the relative stereochemistry of everything else follows. So if you happen to have axial and it's up, then trans is down and cis is up. If I put the bromine over here and made it axial down, then cis is down and trans is up. But the point is that this will only eliminate when you have both groups trans and anti to each other. It's kind of a real, kind of a picky example, but it does illustrate very strongly the demands of this geometry. You have to have these groups pointing like this, or else you don't eliminate. Yes?
So if we just write the chairs, is that a good enough explanation, or do you want us to like write out why?
I would say probably the best answer for this would be the cis isomer has an an actual hydrogen that can eliminate Gibbs-Eitzet product, the other one does not. So it gives a non-Zaitsev product, or something like that, but if you have the picture, that'll be most of it. I forget how much of an explanation I wrote on here yesterday. So I wrote notes underneath that only antiplanar, antiparaplanar is the same thing as anticoplanar. Hydrogen give non-Zaitsev product in trans, and antiparaplanar to give Zaitsev product. So just something that's indicating what you have drawn there, which is mainly just in case you're drawing as a not the clearest.
But it is necessary to draw the chair composition to explain.
Probably not, but I mean, if you don't draw the chair, then you could misremember it, but yeah, I mean, I guess it's, I guess you get by without drawing the chair. As long as it was a satisfactorily detailed explanation. So are there any questions on why with the cyclohexanes that they have to be axial, both axial? I mean, that's basically what it boils down to, is that empirically they both have to be axial.
Weren't there 3 things attached to the first chair composition?
To which one?
The first chair composition? First the methyl and then the
That methyl's behind there, I just kind of missed a little bit, so. The 2 blue hydrogens are what's attached to the front. That didn't work any better, did it? That's CH3, and that's the hydrogen. Okay. So for synthesis problem, this time I gave you kind of a roadmap problem like this, where you basically don't have to strategize how to get to the product, you just have to know your reagents. So basically here it greatly simplifies things, but you do need to know what the reagents do. So the first compound is 1-butine, which I did not draw for you. Not required to draw it, but it's not a bad idea for you to draw it, just so that you know exactly what you're dealing with. But 1-butine going to this compound has the same number of carbons, so you don't need to do anything with that. And the functional group goes from an alkyne to an alkene. That's reduction of an alkyne. We had to go from an alkyne to an alkene, we had hydrogen over Lindlar's catalyst, and we had the dissolving metal, so sodium ammonia. Because this is a terminal alkane, it doesn't matter whether it gives you cis or trans, because it's terminal, they're the same product. If it was an internal one, then you want to remember that the hydrogen over Lindlar catalyst gives you cis, and the dissolving metal gives you trans. But here, the answer you give could be F, and it could also, I didn't give you the other one, so the answer here has to be F. The next reaction is bromination at the carbon next to your alkene. This is a Lillich bromination, that's MBS. It's the only reagent you have that will do that. You could conceivably, especially if I had given you bromine in light or bromine in heat, but a radical halogenation would give that product, but it would tend to give a mixture. But without light or heat, there's no indication that you're doing a radical reaction there. So I would definitely go with the MBS because that's really the only one that's going to be foolproof with that. So then going from top right to bottom right, you are converting an alkene into a primary alcohol. The question you should ask yourself is this Markovnikov or anti-Markovnikov? It's anti-Markovnikov. Anti-Markovnikov hydration of an alkene is hydrochloration, which is K. This is what we used for Markovnikov. On this exam, I just gave you like water and some acid. I don't remember what acid. So basically acid catalyzed hydration. It's not as clean as oxymercuration, but we didn't really cover oxymercuration this time. So that gives you that. The next step is oxidizing a primary alcohol to an aldehyde. So if you look at your oxidizing conditions, they're down here. You have chromic acid and you have PCC. This would oxidize a primary alcohol to an acid. This would go to the aldehyde. So you need PCC for this. And then finally, you want to eliminate HBr to make an alkene. That is typically an E1 or an E2 process. You do have potassium T-butoxide here to do an E2, so that's probably the cleanest way to do it. So that one would be good there. E1 reactions, generally you should have tried to avoid because they're going to have competing SN1 reactions. So usually they're not clean. So it might not be wrong on paper, but it won't be as right as it could be. It's one of those, it's a correct answer, but not the best answer, would be a way to think about that. So again, here you have the benefit of seeing exactly where you have to go. You just have to select the reagent. The tough part with this, of course, is remembering what all the reagents do. And the reagent bank is, of course, naturally set up to give you, okay, these two do the same reaction, but give you a little bit different outcome, and you have to choose the right one for that. So the good news is that you have more information here, and it takes the seeing how to do the synthesis part of it out, which is a big part of the puzzle, and it more or less just kind of makes it a predicted product, or choose the reagent, not predict the products. It's a little bit, same thing as predict the product, but a little bit different direction. So, if you have, well, when you get to Organic 2, whether it's with me this summer or somewhere, someone else, you'll probably start to need to plan, see how to navigate this, not just fill in boxes. But for this exam, your synthesis problem will be similar in format to this. And incidentally, you'll notice that, I had hydroboration and things like that on here. So reagents from previous chapters are fair game. You can't forget what we did back in chapter 6 or 8. So this has reactions from 6, 8, 9, 10. If you have a photographic memory, your roadmap that the textbook has is convenient. So if you can just memorize that, you're golden. But other than that, think of the functional group transformation first. So again, if you chose the reagent that is close but not quite the right product, so say it gave Markovnikov hydration instead of anti-Markovnikov, you might get some partial credit for that, but it would not be full credit. All right, so more predict the product. So per acid was our clue for making an epoxide out of an alkene. This would be something like MCPBA. And yes, the M is a lowercase m, and all the rest are caps when you write it out. I will write this as per acid if I want you to use it, since there were more than one, but they were all per acids. So here you're going to make the chirality center stays the same, and you are going to make the epoxide. The oxygen and its bonds can both be up, or they could both be down. In this case, for optical activity, I would say yes. You get 2 diastereomers, so that it's not a racemic mixture. So unless you're really unlucky, this is going to be optically active. By really unlucky, it would be just the 1 in probably 100,000 chance that they happen to have the opposite rotation. It's probably worse odds than 1 in 100,000, but so I would say that this is optically active. Okay, so the next problem is one of our epoxide reactions. When you have just a nucleophile under something that looks kind of basic, so a nucleophile and no specific acid, for instance. So here we have methanol is going to be the nucleophile, and you have the acid. That gives you a little bit different little bit different result here. Both of them are going to look like SN2 reactions, but the regiochemistry would be different. So here, when you have something that looks more like an SN1 sort of condition, you have a proton source to protonate this, to make it a better leaving group, and you have a poor nucleophile in a protic environment, you would predict that it would react at the more hindered carbon. This reaction does not strictly give a carbocation. You still get inversion of that stereocenter, it just reacts at the more hindered carbon. So here, what you would want to do is you have, when you break this apart, it breaks that way, that bond breaks. And this is going to come from the back side, and I'm going to draw this in plane, so basically the trajectory is here, so instead of these kind of being pointed downward, they're both going to be pointing upward. I realize that's kind of upward, but if we rotate it slightly, it's downward. But the direction it's coming from is here, and so these groups are both moving up from here. Down doesn't get you anywhere. It would be, remember, you want your wedge and your dashed lines to be on the same side of the chain. You don't want one of your wedge lines down here and their dash line up there. So the easiest thing to do is just, if you think of this as being on top, this has to be on the bottom. So if this is on top, this is going to be from the bottom side of that chain. This is the only product. It is SN1 like. It's SN1 like for its regiochemistry, but it's SN2 like for its stereochemistry. So this means that it gives inversion at the more substituted carbon. So this would be optically active as well. You start with a chirality center here, and you do a clean inversion. It should be optically active. Okay, so lithium aluminum hydride, we're thinking of as adding hydride, H minus. This is not an acidic condition, so this is going to be SN2 stereochemistry. It's going to give inversion again. And SN2 regiochemistry. So that means that the hydride is going to react at this carbon. Now the deal here is it gives inversion, but there's already two hydrogens here. You'll never know that it made an inversion. It's not a chirality center to start with, so the fact that it gives inversion is not a factor here. But it does react at the less substituted carbon. So what you would have here is you would these would all be the same. You would have OH here, and the hydrogen you added is that one there. but it would be okay just to write this as CH3. But this chirality center didn't participate in the reaction. The reaction occurs over here. So that chirality center is exactly the same as it was when you started, including the bond to the oxygen. It's just not in a 3-membered ring. So is this optically active? Okay. If you do a reaction at chirality center and it cleanly gives you inversion, it's still going to be optically active. If you do a reaction anywhere other than the chirality center, it's going to generally be optically active. The only time it's not optically active is when you end up with something planar, a planar intermediate, a planar product, so a carbocation, or an alkene. Those are all not optically active. But do remember the alkenes can have stereochemistry. Remember, that's the E and Z. But those are not optically active in the sense that they have chirality centers. So, chirality center, you have R and S configurations, and they can be optically active as long as the molecule is not symmetrical, not meso. Alkenes are flat, so they're not optically active, but you can have stereochemistry, E and Z. All right, so this is a TMS ether, and this is your tetrabutyl ammonium fluoride. So this reaction is occurring out here on the silicon. So the oxygen-carbon bond is not touched. So that stereochemistry doesn't change. All this is doing is knocking the TMS group off of the oxygen, and you get the alcohol out of it. Again, the reaction's occurring out here. The fluorine adds to the silicon, and then you break the silicon-oxygen bond. It does not react at the chirality center, so the chirality center is untouched. So these are, the last two are both optically active for the same reason, which is that the reaction didn't touch the chirality center. All right, so are there any questions about predicting products? The epoxides are probably the trickiest one, and like I said, for the most part, think of the acidic conditions as giving you SN1-like products. Typically, it still goes with inversion, but and then on the other hand, the more basic, just the nucleophile, which is usually a base, that tends to give less substituted carbon and definitely inversion.